Hola, my name is Pamela. Welcome to my channel. Today I'm gonna talk about electromechanical elements. As their name implies, combine the use of a mechanical and an electrical element. They can be a button tube, diaphragm, bellow, or a combination of them. Electromechanical elements are classified according to their type of operation. They are the force balance transmitter, resistive, magnetic, capacitive, strain gauge, and piezoelectric. The resistive elements consist of an elastic element that varies the ohmic resistance of a potentiometer as a function of the pressure. The movement caused by the pressure is transmitted to an isolated movable arm that is supported by the precision potentiometer, which is connected to a Wheatstone bridge. Magnetic elements are classified into two groups, according to their operating principle: those with variable inductance and those with variable reluctance. In those with variable inductance, the displacement of a moving nucleus within a coil increases the inductance as this enters its core. Therefore, the current in the circuit is reduced by increasing the self-induction electromotive force. Variable reluctance ones consist of a permanent magnet or an electromagnet that creates a magnetic field within which an armature made with a magnetic material moves. When this armature changes position, the reluctance varies, and therefore the magnetic flux. With this, we obtain an inducted current in the coil that is proportional to the degree of displacement of the armature. Both types position the core or armature with a mechanical element and use AC inductance bridges wound electrical circuits. Capacitive transducers are based on the variation in capacity that occurs inside a capacitor when one of its plates moves due to the application of pressure. The movable plate is shaped like a diaphragm and is between two fixed plates. Thus, we have a capacitor of fixed capacity and another of variable capacity, which can be compared in oscillating circuits or in Wheatstone bridge circuits. Strain gauges are based on the variation of length and diameter, and therefore of resistance. When a resistance wire is subjected to mechanical stress by pressure, this pressure stretches or compresses the threads, modifying their resistance. There are two types of strain gauges: the bonded and the unbonded ones. The bonded ones are formed of several loops of very fine thread, glued to a base sheet of ceramic, paper, or plastic. In the unbonded ones, the resistant wires are between a fixed frame and a mobile one, under a slight initial pressure. In general, strain gauges have an excellent frequency response, can be used in static and dynamic measurements, are not influenced by magnetic fields, but they have a weak output signal, are very sensitive to vibrations, and have a doubtful stability throughout their operating time. Currently, there are strain gauges with diffused silicon pressure elements. The silicon element is inside a chamber with silicone, being the silicone that is in contact with the process. The sensor is made from a monocrystal of silicon, into which boron diffuses to form various Wheatstone bridges, thus creating a self-contained strain gauge. These are mounted on parts of the instrument that are protected against external aggressions, which allows the instrument that contains them to be very robust and work for long periods of time without maintenance. In turn, they are linked to digital devices with a microprocessor that allows them various functions, such as engineering units, self-diagnosis, and linearization of the output signal without the need for calibration. They are crystalline materials that, when deformed, generate an electrical signal. Quartz and barium titanium are widely used in these elements and withstand up to 150 Celsius in continuous service and 230 Celsius in intermittent service. They are small, light, and of a robust construction. Their response signal to a pressure variation is linear, and they are suitable for making dynamic measurements thanks to the fact that they can give frequency responses of up to 1 million cycles per second. Their disadvantages are that they are sensitive to changes in temperature, to experience zero drift, and to require impedance adjustments in the event of strong temperature shocks. In addition, their output is weak, and they need signal amplifiers and conditioners that can introduce errors in the measurement. Now, I am showing you a table that contains the comparison of the characteristics of the mechanical elements that I explained in this video. So, this will be all for today's video. Don't forget to give me a like and subscribe. I upload videos every Wednesday in Spanish and Friday in English. Adiós! We obtain a...
Ya pues.
Throughout their operating time, throughout their